Good morning, everybody. Thank you very much for joining us today on our high thermal demand soldering panel discussion. We've got a number of experts here today with us. I'll introduce myself first. My name is Chris Shea. Now, on my panel today, we have Mr. Timothy O'Neill, who's the Director of Product Management for AIM Solder. I've known Tim for the 25 years he's been in this business, and he's one of my favorite people to work with. He has 25 years experience and is a certified IPC specialist. His responsibilities at work include developing product and technical information. He's an excellent technical writer and presenter for industry trade organizations and events, and he has been recognized as a speaker of distinction from the SMTA. Our next panelist is Carlos Salinas from Revco Products.
Morning, everybody.
Good morning. Carlos has 17 years of experience in electronic contract manufacturing. He's a production manager, and we all know how challenging that can be on a daily basis, but he leads by example with a very strong work ethic, drive, and a problem-solving mentality. He's well-versed in different skills, which include, but are not limited to, process development and implementation, SMT and through-hole line soldering, X-ray inspection, test, including failure analysis, and conformal coding. He's got a lot of processes under his belt. He's also involved with the recommendation of process equipment qualification for solder alloys and fluxes. He is an IPC A610 and J Standard 001 certified trainer and has been an active SMTA member for 10 years. And finally, to round out our panel is Mr. Ed Zamborski. He's the Eastern Regional Sales Manager for OK International. His position requires frequent customer visits throughout North and South America. I would guess that at least half of the people on this call today have met Ed because he is a legend. And he not only does sales, but he also trains and is the master applications engineer for all OK International product platforms. His expertise includes hand soldering, convection and conduction reflow techniques, array rework, fluid dispensing equipment, and fume extraction. Anything that goes on a rework bench, Ed's the expert. Let's see, he's provided his expertise on a global basis and serves as one of OK's technology advisors to the product development group. He has authored many articles and has presented many papers on topics such as low volume SMT assembly, fume extraction, rework, visual inspection, and lead-free rework when it came about a few years back. So together between the four of us, we have over 100 years of experience building solder joints. And today we want to talk about the high thermal demand. So how do we handle it? Well, in my opinion, we handle it with a process. And it's not just the materials or the equipment in the process, it's the people as well. So I think that's very important. And we're going to look at a process right now of a high thermal demand application. And the video should be running.
All right, when you take a look at this, you guys can see the difference between your potential for reflow between the three different tips. And this is really here to illustrate why you need to match your tip or your cartridge up to the application. I think Carlos could actually hold up an example of what we're soldering, this component.
Yeah, what we're soldering it's a capacitor, a film capacitor, and it's riveted to the assembly. I don't know if you can see it, and then it gets surface mounted to the board, and you solder it with a SAC 305 alloy. And this particular assembly is a lead-free assembly, so it has a big ground plane on the top layer and also the bottom layer.
So you can see you really want to go at this with the largest tip and the most power that you could provide for the application. That's going to give you your best results for this solder connection.
Yes, and actually, we have a question coming in already. When we talk about high thermal demand applications, if this were a low melting point alloy instead of SAC 305, how would that impact the soldering process?
Well, you'd still want to match. Who was that? Was that Tim?
No.
Oh, Carlos.
I've got an answer in my head, but we'll let you tackle that one first.
Well, yeah, when you talk about low melting point alloy, like on this particular application, we couldn't use it because it's not allowed in this case. So if it was different, then your temperature wouldn't be as big, have to be as high, your set points, and then you wouldn't have to use, you could use other fluxes too.
Right, but you'd still want to match the size of the tip or the size of the cartridge as close as you could to the size of the pads. I mean, that's really going to give you the best performance. Tim, you had an answer hiding away there?
I do. Well, Carlos pointed out that it has to be approved for use first. And right now, low temperature alloys aren't in widespread use. And second of all, here's a fun fact about low temperature alloys: not available in flux cored wire in most cases because they're too brittle because of the high bismuth content. So it's a whole new process for reworking with low temperature materials. What are their characteristics when they're combined with other lead-free alloys is yet to be determined. So right now, I don't think low temperature is a viable solution. It may yet be, but as of today, I don't think we'll see too much low temperature alloys introduced in rework.
Excellent point, Tim. That it would change the rework process because we could no longer use cord wire. And one of my thoughts on the topic is the melting point of that little amount of alloy has changed, but the thermal mass that we're trying to heat hasn't.
Right.
So I haven't had enough experience myself with LMP alloys to know, but I know the solder might melt faster, but we still have to heat a whole lot of metal before the solder will melt. So I think it's still the largest tip you can get, and we'll talk a little bit more about irons on our next slide.
All right.
So now let's talk about the importance of preheat when we're in a high thermal demand situation. That's really what I found as a process engineer to be key to getting good rework joints. So
what you're looking at here is you're looking at a convection preheater, and this one happens to be programmable for multiple zones. The graph that you see on the right shows you 4 zones plus a cooling zone. The green line, the lime green, is the actual temperature measured on the device. So the other lines, the red and the blue, are your set points. And this is actually showing you set points for a top heater as well, which you're not going to see on this device. We're just going to use this as a preheater. So what's nice about this is we can program in a ramp rate, which is going to be dependent on the thermal mass of the board, a preheat temperature, and in this case, we're going to set up 4 different ones so that we can gently bring the board up to temperature. And we want to have it up around 150 degrees or so before we start to apply heat from the top. And nobody wants to wait for this, but this does reduce the thermal shock, right? I mean, that's always the complaint. You know, you go to the operator and the operator says, that's great, I don't want to work over this because it takes too long. Well, it takes too long because you're doing the right job. You're doing a good job and you're working with the full capacities and parameters of the solder that somebody selected for you. That's why it's taking too long, because you're doing it right. You know, you can always do it. There's always time to do it over, I guess. That's the way they look at it. But it's always better to do it right the first time. So you want to control your preheat temperature before you apply your fluxes, before you come down with your soldering tip. And I know that I know Tim wants to talk about flux because we know that's an important consideration here.
That's
Tim?
right. Yes, thanks, Ed. Thanks, Chris. Liquid fluxes are most commonly found on the rework bench, but understand most liquid fluxes are the same ones that are used in the wave solder operation. So the operators go over to the cabinet, they take out the gallon bottle of the fireproof cabinet, take out the gallon bottle of flux and start pouring it in. It's no clean, everything should be fine. Well, it works most of the time. It's these outliers where the deficiencies of that become evident. Liquid flux was formulated to withstand a 5 to 7 second contact time at soldering temperatures. In this case, you have a much longer heating profile, more like an SMT reflow profile than a wave solder operation. So there are fluxes, often referred to as tacky fluxes, gel fluxes, or paste fluxes, that would be more suitable in this case. Work with your supplier to make a product recommendation based on your application requirements, but generally speaking, one of the tacky fluxes or gel fluxes will provide enough durability So you can look at wetting in two planes, like a curve. You can look at it as overall activity, which would be the height, and then you can look at how long that activity is sustained. And again, in the case of a liquid flux, it's a very short, high activity operation, not much durability. The paste flux or the flux medium or the gel flux will provide the durability that you need to survive the type of operation that Ed's described here.
So I think, Tim, essentially what you're saying is an application like this, where you're going to see more of a reflow profile than a wave solder type profile, you're better off using the reflow type fluxes than the wave solder type fluxes.
That's precisely correct. And there's another concern that you would have with liquid fluxes, and that's the over application of them. As they're depleted, you keep reaching for the flux bottle and applying more and more flux. That can cause electrochemical problems because you're concentrating the flux in a given area. The flux often requires a thermal cycle in order to be degraded and rendered inert. So those are other issues that using a liquid flux or using the incorrect flux can introduce, in addition to poor solder quality.
Yeah, and I think we talk a little bit more about the proper removal of flux later on in the webinar today. Right now, let's talk about how we choose our tip and our tip temperatures, and how we select our irons. Because profiling isn't always as straightforward as it seems when we're talking about hand soldering or rework, it's really important to deliver the right amount of heat to create the joint you want. So Ed wants to speak a little bit about the graphs we're showing here, which compare inductive and resistive heat, and talk about wattage versus heat. So Ed, I'll turn it to you right now.
All right, thank you. So Metcal, we make inductive soldering systems. That's our specialty. We've been making them since the 80s. So that's where we're going to come to this presentation with that kind of a product. What you're going to see with an inductive soldering system is you're going to see quick rise to temperature, quick rise to set point, no overshoot, very fast recovery. So when you look at these red lines on the charts, you'll see that what's typical is you start at your soldering set point on your iron, you come down onto your load, and you're going to see the temperature at the tip drop down. What you want to see is at the end of that load, which is the end of the solder event, is that the set point temperature then recovers, and it recovers without overshoot. That's what you get with an inductive system. You get a controlled ramp back up. We know that the tip, so we know that the tip or the cartridge, so this is a cartridge. This is one of the cartridges from our GT system. This is one of the fastest tips that we make. We make lots of tips. We make lots of cartridges. But what you want to do is you want to have your tip embedded, your heater embedded in the back of the tip so that you get that fast recovery. You also want to use a high wattage soldering iron. So the GT system that we showed in the first picture is a 120 watt system. So that combined with a tip like this is going to give you fast recovery. If you have an older system like an MX and you're used to, standard tips, I don't know if you can see that. That's a standard 5mm soldering tip, right? You're going to use this for some of your big applications. Well, what we've also done for high thermal demand applications is we've done high thermal demand tips. So if you can see the difference, you can see the difference between the size of the end. Where the working end is the same, the size of the heater is enlarged, and that gives you better performance at your load. In real super high extreme applications, you might have to use a tip like this, which is actually a dual heater tip. So this allows you to use up to 160 watts of power behind the tip. But this is for unusual applications. So you have a wide range of what you can use. But what you'll find with a resistive heater is that it stores energy, so it's slower to respond. The heaters have to wait for the energy to be depleted before the power starts to come back on to heat the tip back up. There's a sensor someplace, and that causes delays. And you can see by looking at that black part of the graph there, is it never fully recovers. So what happens is, as you go from joint to joint to joint to joint, it gets slower and slower and slower. So the time to do, say, 10 connections or 15 connections gets stretched way out with a resistive soldering system, where with an inductive, you can cut off seconds by having an iron that recovers quickly and is able to go on to the next solder joint. One of the questions that we get a lot is, well, can't I just turn the temperature up? And that comes up in a slide later. But every single customer that I go to that wants one of our variable temperature systems, the second question is how do I lock it so my operators can't change it? So we already know that that's a problem. So we don't want to just throw more heat at it. We want to throw more power to it. So keep the heat low, keep the temperature low, and have the variable power to do the solder joint. All right. I think Chris might have even had an example of a high wattage soldering iron that she got somewhere. It's got a red handle. So she's gonna roll that up for you. So if you had
My
your wood
Walmart
burning kit,
iron
right? So she got
to
that.
Walmart.
There you go.
I had a rescue who liked to chew electrical cords. So the Walmart iron and actually samples of AIM flux cord solder when I was back as a process engineer. I used to fix a lot of chewed up wires from Riley.
There you go. Well, we got to get that soldering iron upgraded for you. That'll be my goal by the end of this teleconference.
You know, I wouldn't mind a nice iron for
There you
attaching
go.
thermocouples now and then.
And we'll make sure that it's inductive and not resistive.
There we go. Well, you know, there's something I want to point out about the inductive iron is this is the thermal pattern we see at the tip when we put a load on it and when we recover. And when I look over here, I see how repeatable that is.
Mm-hmm.
And when I look at resistive, that's not repeatable. And I'm really into process control, and I love seeing repeatability like this.
Right. And you know, the problem there is so each solder joint that you do after the first one with that resistive iron starts at a different starting point. So where's your process control? You know, you want it to be starting at 350 or whatever your set point is every single time. You don't want to start at 350 and do the next one at 320 and then the next one after that at 310, because now you've lost all control and you can't tell your operator, especially a new operator, well, solder for 5 seconds or 7 seconds, because it's changing. You're chasing a moving target.
You are, and I've found a lot of times they just want to push the solder iron in harder, like, you know, like if you keep pushing an elevator button, it'll come sooner. And they'll push your soldering iron in harder, or they'll turn it up and they'll end up delaminating the board locally.
That's right.
So, you know, this data talks, and this is a nice repeatable profile. I like that a lot. And again, if we go back to our old reflow adage of heat is all energy is all area under the curve. Again, we've got a lot more energy that we're putting through in a much shorter period of time. So I like everything about that. The process engineer in me does. Now let's talk about flux. And we alluded to this a little earlier about using gel flux, so we don't flood liquid flux under components and not give it a good thermal excursion to activate and deactivate. So now I'm going to turn this to Tim for a while to talk more about fluxes.
Great, thanks, Chris. Oddly enough, I got a email this morning, exactly this scenario, and they're asking for advice. So I'll give him the answer. He's a participant because it addresses a thermal mass challenge with the added twist of a solderability issue. So how do you solve that problem? Speaking specifically to the thermal mass issue, as I mentioned earlier, liquid fluxes aren't formulated for rework. We have products that are formulated for rework, and the concern and what differentiates them from reaching into the fireproof cabinet and grabbing whatever flux is being used on the wave solder machine is that a liquid flux, generally speaking, needs to see a thermal cycle to be rendered inert. The acids that are used as the fluxing agents or the activators are decomposed at temperature, and they lose their electrochemical concerns are greatly diminished. That's how a no clean is quote unquote activated. We can formulate materials that have buffering agents in them that reduce their electrochemical issues without heating. So we have a couple of fluxes that are specifically formulated for rework. They're not great wave soldering fluxes. They're specifically formulated for rework. So it's a subtle distinction, but one that's worth noting. And that is, use a product on your rework bench that was formulated for rework, even though it looks exactly like the flux that's coming from the wave and is called a no clean. There is a difference. So the problem with the high thermal mass boards, or the challenge, is that the long cycle time. So there's a lot of heat being thrown at the soldered surfaces, and as I mentioned, heat degrades liquid fluxes, which is a good thing if you're worried about electrochemical concerns. It's a bad thing if you need the flux to stay active throughout the duration of the solder cycle time. That's where the gel fluxes or the tacky fluxes may offer some benefits. They are formulated to withstand reflow profiles, so 4 or 5 minutes at temperature, doesn't degrade them as rapidly, and they'll give you the survivability. The downside is that the agents that are used will typically result in more residue. So after soldering, unlike a liquid flux, which might be 96% IPA, there's only 4% solids left behind. A typical rework flux or gel flux or paste flux is 50% solids. So there's a lot more gooey stuff post soldering. So there's an aesthetic issue with that, not necessarily a reliability issue. It's less aesthetically pleasing, and for an EMS provider, that's often an indicator of quality. So now the next thing is, well, now I've got this extra residue, how do I remove it? And that presents its own challenge. Now, I'm not a cleaning expert, and I defer to the cleaning experts when it comes to these issues, but I've worked with them often enough to understand what their recommendations will be. I always suggest collaboration with a cleaning company if flux removal is deemed mandatory. Again, as the solder supplier, my fluxes will pass unheated. My rework fluxes will pass SIR unheated. So the removal of residue is really an aesthetic issue for me. In fact, incomplete flux removal, I would say it produces a less reliable product than either a residue that's left completely untouched or residue that's been completely removed. That middle ground is where most people end up. And in the image that's on the slide here, that looks like flux residue that was either over applied or incompletely removed. That white hazy residue is pretty common. In our testing internally, we've attempted to remove flux residue with isopropyl alcohol, which is a common solvent you'll find on rework benches. And the SIR performance, or the insulative properties of the flux after cleaning, will fall a full decade from material that was left untouched. So we formulate our products to be uncleaned. That's why it's called a no clean. I can't account for what's left behind after a residue's been partially removed. I don't know what the electrochemical properties of it are, if it's done properly. And further compounding it is that there's a lot of operator involvement when attempting to remove flux residues at the workbench. So that's a great opportunity for dirty brushes to transfer contamination from the brush to the workpiece, and just a lot of opportunity for improper processing and handling. You guys mentioned process control. The least operator involvement, the better, as far as I'm concerned. But if I got to clean, I go to the companies that are promoting flux removal products, engineered solvents specifically formulated for this application. They are not IPA. They are IPA plus, a bunch of other solvents that do a good job of removing the flux all at once. And we have residues there. We have to remove all the residues in the first shot. Once a residue appears, it gets harder and harder to remove, because what you're leaving behind is the least soluble components of whatever's there. So you're concentrating the least soluble stuff, and it just gets more and more difficult to remove. So an engineered solvent, properly used on a gel flux, if it's got to be cleaned, that's my recommendation on how to use gel fluxes properly, which might be required for a high thermal demand application. And if you got to clean, use an engineered solvent.
Excellent. Thank you, Tim. And just to go over this image here again, what this was a no clean flux cleaned with IPA and an acid brush. It
Mhm.
was a manually added on part, did not need to be cleaned. You can actually look up in here and see there's still a little bit of the resinous residue up there. And to your point, all this white stuff is ionic material that's been unencapsulated. It was protected by the rosins. Now we've dissolved away what's protecting them. And because I could only take a small picture of the board, so there's nothing identifiable to the OEM, because they used IPA with an acid brush on this and put it back in the rack wet, not only is this small area of the circuit board contaminated, but about a third of it from where that alcohol with
Drip.
partially dissolved flux ran down under other components. And it's really no surprise that there have been corrosion issues with this product. So that's my soapbox on IPA. Let's go back to Ed for a minute and talk about contact area and choosing our tips.
All right. Well, I said this a few times today, but what we really want to do when we're selecting a tip or a cartridge for our application is to get the tip as close in size, and also when we look at those tips, we want to look at the geometries. We want to make sure that we have double flat tips. We want to make sure we have a good selection. Any of the tips that I'm going to try to show you here, of course, they're going to be hard to see because of the lighting and because we're not doing this live. But the bottom line is you want to match the tip to the geometry of the pad, okay? We also want to use the most powerful that we can, especially on a high thermal demand. So I would go for something with a larger heater. One of my GT systems would look something like this. This is just the heater taken out of the handle just to make it easier to see. So on a GT system, you can select between a high performance tip or an ultra high performance cartridge, depending on what your needs are, what your budget is for consumables. So there's lots of assortment for matching the tip to the job. Here's a couple of real extremes. And these would be, we talked about rework before, so these would be for use with desoldering braid, right? Or if you wanted to try to do multiple leads at a time. These are made with higher masses, so we do two different sizes. You can see the one, let's see, on this side is a little bit higher mass because we know that we're going to have thermal losses when we go down onto a piece of braid. So these would be for multi-leads. You could use them for BGA cleanup. You could use them for the QFP that we saw before. And like I said, if you have an extreme, you can always go to something like this, which has, you know, 2 heaters, very large mass, so that you can get on and off that load very quickly. So there's a lot. I warned Chris I was going to bring props today. When we did this on Friday for practice, I was just using my hands, but today I decided to bring some props. So, you know, they're all easy to change. You know, you can get in there and plug them in and unplug them very easily, but you want to make sure that, you know, you're matching that tip to the job, no matter what it is. You want to be able to go in there and say, okay, I've got exactly what I needed. I've got the same handpiece. I can plug it in, take it out, use it however I need it. And really, you want to have the most contact area. And that's important. When I go onto a load, this is one of my favorites. This is a tip that comes off of my GT system. This is a high load that I've done many, many times for Zoom demonstrations. It's kind of hard to see here, but it matches that load, which in this case is a terminal strip. So not only do you have the load of the board, but you have the load of the hardware on the other side. And this does an excellent job at soldering it quickly, efficiently, all the way across the board. And that's because we match the tip. I don't want to do that application with a tip like this. I don't know if you can see this. Let's see. You can see the loads, and you can, I don't know if you can see how small this tip is, but this is really like the middle example on the graphic. You know, somebody going in with a tip that's way too small and then wondering why it's taken so long to reflow that solder joint. And that's what we want to avoid, because you're not going to get good results. You really want to make sure that you get in there and match it to the load. Cartridge versus tip, that's number 2 there. I picked it up before. This is a replaceable tip. You can see it's a small, inexpensive consumable. That's a replaceable tip that goes onto a heater that's mounted in the handle. everybody's familiar with this. It's been around for, 100 years. The benefit here is you get great performance and you have a lower cost consumable. When you get onto that higher mass, then you would go to a cartridge, cost you a few dollars more, but easier to change, and you can get the full capacity or the full performance of that station. So that's really what you want to do. And then, like we said before, you want to match that contact area to transfer the heat. We could talk about this. I could talk about this slide all day, and I'll see people quickly dropping off. So I'm going to hand it back to you, Chris.
Well, Carlos is not that none of you guys or myself are process experts, but Carlos is our resident true process expert for this webinar. So let's ask him to talk a little bit about cartridge versus tip, and actually about this application that is a crazy, crazy heat sinking heat source application. Carlos?
Yes, as you can see on this slide, this is a aluminum substrate, and it's an LED panel. And it's very common with these LED panels that once the substrate is real thick, and I have another sample here too. I don't know if you guys could see it, but it's, and what happens with this is a lot of the times you have to add parts after the reflow or the wave solder process. In LED panels like the sample there, you usually have to put some wires, solder some wires to it. And then one of the challenges that it's not to melt the insulation or choose the right insulation for it. So on that case, I will recommend a Teflon insulation. One of the other challenges that we see often is how do you get an acceptable barrel fillet? So on that, whenever you could automate it, you run it to one of those processes. But like in every case, there's always parts that you have to put by hand, and that's where we go with the largest tip we could use, and also a water soluble process. So if you can't, then you have to wash it, and you got to make sure you don't exceed component temperatures. So your set points will be a little bit higher. One thing to note is your process becomes larger. So you gotta preheat a little bit longer. You gotta cool down after. Like on the aluminum substrate, it stays hot for a while. So if someone's doing it on the bench, then you gotta wait for it to cool down before you even remove it. There's a safety concern there too.
All right, and then let's take a look at this next image, which is pretty striking. This is taken with an infrared camera on one of your applications, Carlos. Why don't you describe what we're looking at here?
Yeah, what you see here is it's a large board that has a big power plane on the top side and the bottom side, also in the inside layers. What you see there is the soldering iron, and it's touching a soldering pad. But you could see how that heat gets transferred. It's like a heat sink. It starts joining. And then if you look at the bottom right corner, because the plane is attached to the thermal plane, you could see how it's getting hot. So the whole board is getting hot, and you could see that on the bottom right corner.
Yeah, and this is a fantastic image. Thank you guys for taking it and pointing out that we just really don't know where the heat is going when we put the iron to the board. I have one of these little cameras, these FLIR modules that snaps onto my iPhone. I use it all the time to find the hottest and coolest spots on the board when I'm reflow profiling. So it's a handy little tool that's a couple $100 that perhaps your boss will let you buy because it's worth every penny. Moving on, let's talk about some of the reliability issues. And while we're on this, I have a question that came in about fluxes, asking if liquid flux is designed for selective soldering processes where longer dwell times occur. Could those be a viable alternative to gel fluxes for rework? Tim?
I hate this answer. It depends. But it depends. I would be more than happy to review the flux attributes and try and give some insight as to what you'd expect for its performance. But generally speaking, point-to-point selective solder operations, a lot of the same concerns that you have with rework, where flux can be applied in places where it doesn't get thermally degraded, so they tend to have a higher safety profile. I don't know the flux specifically, so it's hard for me to give you a definitive answer. But in general, fluxes formulated for selective should have a higher safety profile than fluxes that are for full wave. Check with your supplier, see what kind of answer that they can give you.
And in terms of surface insulation resistance, what are we looking for, Tim, when we're looking for a selective solder flux?
So per IPC J standard 004B, 100 mega ohm is the minimum requirement per the SIR testing. The test actually branched off in 2008, maybe sooner. I'm sorry, forgive me for not knowing the date. But there's J standard 004 and J standard 004B. The environmental conditions were modified in the 004B or the later spec to 4090 versus 8585. I don't want to get in the weeds, but suffice to say, having evidence that the flux passes both of those tests is a belt and suspenders approach to a safety profile for that flux.
Exactly. That just came up actually with me, with one of my clients on Friday. The importance of being able to make sure that's electrochemically safe and looking for higher SIR numbers in certain cases, like instead of 100 mega ohm, which is 10 to the 8th, looking for 10 to the 10th, just to make sure. Also, we talked about, because it's not going to be fully processed, what we talked about is looking for the comb pattern up SIR results, which is more indicative of under process. But
and it should specify unheated, because that is not the test. The IPC test gives you heat it. So
yes,
you know, it's not an IPC standard to test the fluxes unheated.
No, and there's also a big, well, there is a difference between 04 and 04B, and it's a lot more difficult to get an L0 rating on your flux under the 04B protocol. So
I would agree.
When people are looking at that L0, they need to make sure that it's under 04B and not the original 004, where it's grandfathered, and it could be a lot more active. Its residues could be a lot more active than if it were tested under the 04B protocol. We'll get out of the weeds now and talk about mechanical reliability, how we form intermetallics and good solder joints versus cold solder joints. We can throw that to Ed. We can talk with Tim a little bit more about encapsulating or washing flux residues, because we're beating that horse to death for a reason. And I can just go back to, it's all about controlling your process. So Ed, Tim, Carlos, talk about process control to make sure you get good joints and electrochemically reliable ones.
Go ahead, Carlos. You look like you're ready.
Yeah, well, whenever you go repairability, right? So if you're using the same equipment, you make sure everybody's using the same tip, the same fluxes, and if you do that, you got to profile your assemblies before. Always check that out and make sure you know, you're meeting your reflow temperatures depending on the flux or the alloy you're using. So yeah, if you could do that and repeat it through every station, then train your employees. It's very important. And like I mentioned before, if you can't get away with using a water soluble process, do, because your process window becomes twice the size an old clean wood, especially for these high thermal demand assemblies.
Okay.
Yeah, we go back to exactly what Carlos said. You know, it's about training. You know, it's about training. It's about equipment. It's about selection of the components. If you're not using the right solder and the right flux, you could have the best station in the world. It's not going to do the right job. And if you don't train your operators and you don't retain your operators, you just add another big variable. So I mean, buy good stations. I mean, we make connection validation stations that'll let you verify the intermetallic by a power curve. So I mean, there's a lot of options. You know, it's not just the plug in the wall iron that Chris showed before. So it's important that you have good equipment selection. You know, and then that leads right into Tim with his flux selections.
And we got a question in regarding that, asking, does water soluble flux have reduced thermal longevity and high thermal demand applications?
Generally speaking, water solubles, as Carlos mentioned, do open the process window considerably. However, any residue that's left behind, well, let me take a step back. Usually no cleans are used on the rework bench because the reason you're hand attaching a component is because you couldn't wash it in a wave solder operation. So the viability of water solubles on the rework bench is somewhat limited because you can't rewash the board. Otherwise you wouldn't have used, you would have built it that way in the first place. So the hand cleaning water soluble fluxes is not recommended. I'm strongly recommending automated wash processes for water soluble flux residues because they are conductive, they are corrosive, and they will, not might, will damage the board if left behind. One of the big reasons that water solubles have become less common is not only the cost associated with cleaning the boards, but also as devices become lower and lower standoff. I mean, essentially, we have 0 standoff devices now. So you can often get wash media under those components, just very difficult to ensure that you're getting it out. So that's my concern with water solubles. But in terms of solderability, they'll solder rusty nails. So, you know, if you can get away with it, I agree with Carlos, go for it.
I think that question may allude to early on when we went lead free, we found out our water soluble reflow fluxes weren't getting us where we needed to be in the higher temperatures, but newer ones have been reformulated to address that. So if that's part of where the question originated, we have conquered that as an industry. So let's talk a little bit more now. We had some frequently asked questions about soldering irons. So I love the one, can we just use 2 irons for my high thermal demand applications? I guess if you have 3 hands, but what we see here actually is an iron that didn't quite have enough energy to melt the solder. It got itself stuck in the solder, and now a rescue iron is coming after it to help get it out. So Ed, why can't we just use 2 irons for high thermal demand applications?
Well, like you said, Chris, we don't have 3 hands. We can use 2 heaters in the same iron, but we can't use 2 irons unless you're doing a very specific task like those chip components and you want to use 2 irons instead of a pair of tweezers. That's the only place that I would see a use for this on the board, and they would be 2 matched irons, right? They'd be this 2 irons with the same size tips, the same size heaters going in there, and you'll see the operator go in there like this and pull them off the board. What we saw there was, you know, like you said, we have an iron that's stuck to the board because it didn't have the thermal capacity to do the solder joint. And now we do have to come in with that rescue iron. So this is not, you know, this will happen. This will happen when you use your plug in the wall iron or you use some 40-watt iron because, oh, you want to protect it. So you're going to go in there with the iron that you happen to find laying around and it just doesn't do the job. So what can happen, and this is a great example, if I don't use a high thermal demand cartridge, it's going to slow the process down and it can cause the iron to stick to the load. You don't want to do that. Can I use a high-powered cartridge on a standard application? Absolutely. All of the inductive irons that we make are variable power, right? They're fixed temperature variable power. So if you only need 10 watts, it just delivers the 10 watts, right? The whole job of this heater, I don't know if you can see this, the whole job of this heater that's embedded in the back of this tip is to maintain that tip temperature. It's going to deliver however much power through those wires to get that to maintain that tip temperature. So that's the whole goal of this system, is to maintain that tip temperature. So if you need 80 watts, you'll get 80 watts. If you need 120 watts, you'll get 120 watts. But if you only needed 15, that's all it's going to deliver. So that's an important consideration on the high thermal demand applications.
What if I have a mix of high thermal demand and typical applications? Do I have to switch out cartridges?
You can. I mean, more likely it's going to be what you see on the board in front of you, where you're going to have to go from, now I mixed everything up, where you're going to have to go from a wide tip like this to a smaller tip for a different application. So if everything was about the same size, you could get away with one larger tip. But because you have your surface mount components on there, you'll probably have to go to something a little bit smaller for some applications. So more likely you're going to change for geometry more than you are for power. right?
Okay,
Because
that
the
makes sense.
stations are variable. They're going to deliver as much power as you need, but more likely it's going to be the geometry of the target.
Why can't I just take a really high wattage iron and max it out at 900 degrees? Won't that work?
Well, it's going to melt the solder, right? It's going to melt the solder. It's going to oxidize the tip, probably damage the joint. It's going to damage the coatings on the board, could delaminate the board. So yeah, it'll work, but it'll also create a lot of rework for the people further down the line. So you don't want to do that. I said that before. Every customer that I go into with a variable temperature station like this, the second question is always, how do I lock the temperature? Right? So we know that 900 degrees is not a solution, right? You can have whatever temperature you want and you can lock it. And that's what you get from, our systems, our inductive systems, is real process control. That's what you want to get.
Okay, that's an excellent answer. And now the next one. How do we remove solder? Do we add more thermal mass by putting wick to it when we have one of these high thermal demand PCBs? How do we actually, maybe that's a good question for Carlos as well. How do we get the
what do you
solder
guys
out?
do?
Yeah.
Yeah, the process is the same when you're trying to solder it, but now your mass is a little bit larger because now you have solder there. So same thing, you gotta preheat it. You gotta use something that has a high wattage, and when everything some vacuum tool, they'll get the solder out, which is heated, of course. And then if everything else fails, then you could use a low melt alloy, and you coat it with that first, and then that reduces you don't have to use as much heat to remove that solder.
So you basically take down the melting point of the alloy
Yep.
and then suck it out.
So
I
yeah,
like it.
But then you gotta clean all that residue off the board, though. You gotta make sure you do that, Carlos.
yeah, that's the unfortunate part.
People
That's
freak
what,
out.
yeah, that's what makes our windows a lot larger. It takes longer to build something when you're reworking it.
Oh yeah. I think Ed mentioned earlier, never enough time to do it right the first time, but plenty of time to rework it. That was my
That's right.
experience with contract manufacturing. And we talked a lot about tip sizes and tip shapes. I think we talked more about size than shape. Why is the shape important?
Well, you want to get as much contact area from the tip to the load, right? Every operator I go to wants some kind of a conical tip, right? They want some conical skinny tip like this because they have a couple of applications on the board where they've got to get around something or into something. But the reality is the surface area between these two tips is dramatic because of how much flatter, I forgot this is backwards, is how much flatter this is. So it matches the load. If I'm going to go in there onto Carlos's capacitor, I want to go in there not with something that has a tiny pinpoint at the end. I want to go in with something that's big and flat and able to do to match up that geometry to that load. If I have no choice, I'll go with a conical, but my choice is always going to be a double flat or even a chisel style tip. I mean, those are pretty common. You'll see those everywhere.
Yeah,
Well,
and
the
for
more
us, we like chisel tips. Those seem to work the best for these high thermal demand applications, especially because a lot of the times you're dealing with a large surface area, so the chisel tip works great.
Yeah, and you get that match, that geometric match, and you get the best heat transfer. So that's really the direction you want to go.
The more metal to metal contact you get, the better your heat transfer is going to be. So it just makes sense from that perspective. And finally, let's just talk about tip care and usage. This is one of my pet peeves in factories, watching around and seeing irons that are still on or tips that are untinned. I get a little hot under the collar when I see that. So Ed, you're a professional. Let's talk about proper tip care and usage.
So if you notice the used tips that I brought out before, I don't know if you can see, notice how you can't spot the geometry. You can't tell what they are. Wait, hang on a second. Let's see if this is any better. You notice how you can't tell if it's a conical or double flat or a chisel? That's because I'm trying to make Chris happy So after I used this for a demo the other day, what did I do? I tinned it and put it away, right? Because think about it, you've got this iron surface. Just like if you scrape the paint off the fender of your car, it's gonna rust, it's gonna oxidize, right? So you've got to protect it with the solder. So after you're done with it, now all the all the new tips that I show you, right? They're all nice and easy to see the geometry. You can tell what they look like because those are all tinned at the factory. They haven't been cleaned off yet. So on top of that iron plating is a layer of solder, so that protects the tips. So how do I want to clean it? I mean, one way is to use a wet sponge. That's what everybody's been using for 100 years. We give you both options. You can use the coiled brass or you can use the wet sponge. I mean, the wet sponge is definitely going to thermally shock the tip. So the tip is sitting up there at 800 degrees, and the water is sitting at room temperature, right? So the water is at 70 degrees. So you're going to thermally shock that tip every time you hit it into that water. You're going to develop surface cracks in the tip, which are eventually going to let the flux into the copper base of that tip, and it's going to start to erode that. So that's going to affect your tip life, which is going to make tips more expensive for you. You can also use a tip cleaner. We make a tip cleaner, which you see in that picture right there, the one on the right, which when you put the tip in, it automatically starts the brushes and it cleans the tip off. So you're not thermally shocking it, and you're not using a super high abrasive like a lot of people will try to use, even a stainless brush, which could be very very dangerous for tips, right? And the other advantage, I'm pointing to the screen, which is a big help over here, but the other advantage of using that cleaner is any of your solder splatter or residue stays within that chamber. So you have a little silicon crosshair that you pass the tip through. So any of the FOD from the tip stays within the device. You could empty it out into the recycling. Tip tinners, those Tim can talk about what makes those up. Those they used to be like the scrap, the overrun of solder paste, right? So you never really knew what was going on there when you stuck your tip in there. It comes out really clean, but that's probably because there's a really acidic flux in there. So in extreme cleaning operations, you could use a tip tinner, but it's really going to break down the coating on your tip and cut down on your tip life. Cartridges versus replaceable tips. Well, a cartridge, now I lost it. A cartridge is going to be easier to change, right? I showed you that before. You could plug this in and change it really easily, really quickly. A replaceable tip, though, on the other hand, so you have a little extra piece you got to take off. Is that really the end of the world? You don't change them that much anyway in production, right? So if you have a production iron that uses the same tip day in, day out, switch to a tip because the cost of your consumable is going to be much less expensive, right? This is about a $10 consumable versus a comparable tip like this is probably about $20 or $22. So if you can use the tip is going to save you money in what I like to call the feeding of the iron, right? Because you have to feed this iron, and you'll save yourself a ton of money if you can go to a replaceable tip. So I mean, it comes down to what your changeover is like for each operator. You know, if they need the cartridges, you go with the cartridges. Wherever they can use a replaceable tip, you want to get them to a replaceable tip, save yourself some money.
That makes a lot of sense, Ed. Thanks. I just want to let you know that even though I haven't used this iron in 3 years, you can see my tip is still tinned.
Yep, see, that's good.
So now we've got a few minutes for closing comments from everybody, and I wanted to put our contact info up here again if anybody has any follow-on questions after the webinar closes. Here, so you can get a hold of any one of us. Also, if you have any questions right now, you can type them in over the next few minutes. We've got about 5 minutes left for some closing comments. I'll start with Carlos.
Yeah, from our side, I didn't mention this earlier, but also just choosing the right finish for your fab or your substrate. I know in our experience using a INIC finish it works better on high thermal demand than like a hassle finish would, because you're not introducing an extra thermal cycling on the bare fab to start with. So that's important. And again, we use an inline cleaner for most of our process. So that's why water soluble. But I see this happen a lot with some of my customers. Says they try to use a water soluble and they don't clean it with water and heated water by that case. So that's a problem. If you do go with the water soluble, you got to make sure you clean it the proper way.
All right, thank you. Tim, final thoughts on alloys or fluxes?
I just want to thank you and the other panelists for their contributions today. I learned a few things, so that's always cool. I would say that the rework bench where this is happening is the least glamorous and most overlooked location on the production floor. Engineers gravitate to the equipment that beeps and tells them data and tells them things, but the rework bench is a management issue, and that's not very exciting and the most difficult to execute. Don't overlook it, because if we have an electrochemical failure, the first place I walk over to is the rework bench. It's the highest level of operator involvement, the greatest opportunity for unapproved materials to make their way onto the product, and it is the last place in the process that people touch. So if it's the least likely to get caught. So pay close attention to your rework benches, not just for high thermal mass applications, but for all hand soldering operations, and you'll have a happier life. I guarantee it.
Thank you, Tim. And Ed, it's 12:59. You get the final word.
I get the last minute. It's good because I didn't prepare, so a minute's good for me. I said it a million times, pick the right tip to match the application. Use an inductive soldering system so that you get the fixed temperature, variable power that you want to get for your application. So you're not guessing what's happening. It helps you control the process. Rework is important, so is production soldering. You want to control every step along the way. Use good equipment, train your operators, and retain your operators. That's super important. Again, if you have any questions, there's our contact information. We'll be more than happy to answer your questions either in the last 30 seconds or moving forward. So reach out. There's a lot of material that's available for our customers. Thank you.
All right, and with that, we are right at the top of the hour. I don't think we could have planned the timing better if we tried. I would like to thank our panelists, and I would like to thank the 150 plus people who joined in today to listen to our fine webinar on high thermal demand rework. Again, if you have any questions, you know where to get a hold of us. All our information is right here for both email and LinkedIn. Thank you all for attending. Hope you have a wonderful rest of your day.
Thank you.
Thank you, everybody.
Bye-bye.